All right, grade 11 chemistry. Here we're talking about stoichiometry with masses. So we're getting into the actual stoichiometry part of stoichiometry. We're going to be converting masses of a reactant to masses of a product. Here's what we're going to actually do. We're going to first review, excuse me, we're going to review why do we use moles instead of masses. Then we're going to look at some concept maps, just a concept map of how stoichiometry works. Then we're going to talk about the actual process of mass-to-mass stoichiometry, which is the process of determining theoretical yield. So we're going to do some practice problems that involve determining theoretical yield. And then we're going to talk about percent yield to finish off our lesson. So I'll put that away and let's talk about the first thing. The first thing is, why do we use moles? I want to harp on this again. Why do we use moles when we compare things instead of mass? Well, here's an example. Here is thermite. Thermite is iron oxide, this is the red powder, rust, and aluminum, powdered aluminum. And you want to mix them to make your thermite, the thermite reaction. And here is the balanced equation, right? 1 Fe2O3, 2 aluminum. So it takes 2 aluminums for every 1 Fe2O3. So 2 of these aluminums for every 1 of these Fe2O3s, 2 moles of this for every 1 mole of this. But when we get to the mass, if you want to do a mass, you're not going to do two masses of aluminum to 1 mass of iron. It's not going to be like 2 kilograms of this and 1 kilogram of this. No, it's going to be actually pretty much the opposite. When we look at the actual ratio that we need to mix things in, it's 80 of the iron oxide, it's like 80 grams of this, and 27 grams of the aluminum. So even though there's 2 moles of aluminum, in terms of mass, the aluminum has to be a much smaller part of this thing. Why? Why might the aluminum be a much smaller mass part compared to the iron oxide, even though it's twice the moles, twice the amount of elements? Well, let's look at our good friend, the periodic table. When we look at our good friend, the periodic table, the aluminum has a mass of 26.98. The iron has a mass of 55.85, plus there's oxygens attached to it, right? There's the aluminum is relatively low mass, iron has a higher mass, plus there's oxygen, plus there's 2 irons there. So this is just a heavier chemical. It's a heavier chemical per mole, much higher grams per mole. So even though we need more moles of this stuff, we need more mass of this stuff. That's where the 27 to 80 comes from. So when we have the equation, we can't use this to figure out the mass ratio. We need to know the grams per mole. We need to know how much these things weigh before we can actually figure out the mass ratio. That's the first thing, right? Explaining once again why we need to do moles. So the next piece here is going to be talking about some concept maps for stoichiometry. Okay, so here's a concept map. Concept map for stoichiometry. And this is showing us what kind of conversions we can do. And it even tells you what the thing is to do the conversion. And guess what? We've already seen each of these steps bit by bit. Video 3.1, we were talking about converting from number of particles to number of moles with Avogadro's number, which is that 6.02 times 10 to the 23. Right? We can do that. We can go back and forth from moles of something to particles of something. So from number to like a billion of something, things like that. And same thing on this side, moles of B to particles of B. Both of them use Avogadro's number. So I have 3 moles of A and 3 moles of B. I have, the same number of particles of A and the same number of particles of B. So that was video 3.1. Video 3.2, which in video 3.2 I said this is the most important conversion. Video 3.2 was the mole ratio, converting the moles of A to the moles of B in a reaction. Right? So that's the most important piece because it connects A to B. We can link A to B. And if you look in the keep in mind up here, we can only convert one chemical to another effectively if we use moles. So we want to convert moles of A to moles of B, we need the mole-to-mole ratio. 3.3, yesterday's video, was all about molar mass, determining molar mass, and then using it to convert grams to moles, and moles back to grams. So in each of our videos, we've uncovered a small part of this concept map. Today, what we're going to try to do is go from mass of A to mass of B, right? Mass of A to mass of B. But the only way to get there, as it says up here in the keep in mind, as it says up there in keep in mind, is to go from mass of A to moles of A, from moles of A to moles of B, and from moles of B to mass of B. And importantly, we've already done each and every one of these steps bit by bit. We're just going to chain them together into what I like to call three-step stoichiometry. Step 1, step 2, step 3. Here's another look at a similar thing, same kind of concept, but here it's even telling you that there's a volume one too. You can have moles per liter, for example. So you can go from mass to moles, moles to mass. You can volume to moles, then to moles, then to volume. You can go volume to moles to mass if you want. You can move your way around this map any way you want, but no matter which way you go from A to B, you are going to have to go through the mole ratio at some point. The mole ratio. And that mole ratio, as we've learned, comes from the chemical equation. It comes from the chemical equation. So for example, in thermite, the mole ratio of iron to aluminum is 1 iron for every 2 aluminums. If we have 4 moles of iron, we're going to need 8 moles of aluminum. Right? That's that central piece of all of our conversions. When we go from A to B, we have to use that mole ratio. Yeah. So that's 3 steps. I call this 3-step stoichiometry. Step 1, step 2, step 3. And it's pretty much always 3 conversions. Step 1, step 2, step 3. Step 1, step 2, step 3. Step 1, step 2, step 3. Whichever way you want to go through it. But we can't avoid that middle step. Most important step. That's the one that requires the reaction. Okay, so here's kind of a view of how we're going to do it. Quick little example of it is start with the amount of your known, and that amount can be a number of particles, a mass, or a volume. Take it to the moles of your known. How many moles, right? How many moles of A? Then from moles of A, you're going to go to moles of B. That's your unknown. Uses the mole ratio. Moles of A to moles of B, always the mole ratio. And then from the moles of B, you can figure out the amount of B, like the mass of B, or the particles, or the volume, or whatever. That's it. So right now, we're only interested in the mass part of the equation. We're only interested in this middle piece on this concept map, mass to reactants to mass, or here, this top part, mass to moles to moles to mass. That's going to be our 3 steps. That's breaking down our 3 steps. So we're going to do a practice problem. Let's try it out. So let's do a practice problem. Practice problem here is we have 4 grams of H2, 20 grams of O2, and here's our reaction. Here's our reaction, 2H2 plus O2 to 2H2O. And the question is, how much water can we make with these starting materials? How much water can we possibly make? Well, I've got that set up over here. I've already written it out. 2H2 plus O2 makes 2H2O. Oh, I should put up the current topic and the keep in mind. And we're not doing concept maps, we're doing a practice problem. That I've put up the molar masses, 2.02 grams per mole for the H2, 32.00 grams per mole for the O2, and 18.02 grams per mole for the H2O. If you don't know where these are coming from, please watch the previous video, video 3.3. That's where we talked about getting grams per mole for various substances. So we have 4 grams of H2 and 20 grams of O2. Now remember, we can only convert one chemical to the other effectively in moles. So what I want, I've got 4 grams of H2, 20 grams of O2. What I want is to figure out the amount of moles of H2, amount of moles of O2. Moles of H2, amount of moles of O2. And this is what we were practicing in the previous video. We were practicing figuring out how to get there. The way that we did it was with conversion factors. We multiplied by, on the bottom is going to be grams, on the top is going to be moles. 1 mole, it's 2.02 grams per mole, so 1 mole per 2.02 grams. So I'm dividing by 2.02 grams. My 20 grams of oxygen, same idea, 1 mole per, and it's the mass of the molecular weight of oxygen, 32 grams per mole. I'm doing 0 grams. I'm dividing by 32. Here I'm dividing by 2. And so what I'm going to have is some number. So I'm going to get my calculator out, wherever I put it. Here it is. Something dropped there. 4 divided by 2.02. That's 1.98 moles. 1.98 moles of H2. And 20 divided by 32 is 0.625 moles of O2. 0.25 moles of O2. So that's our first step, is figuring out how many moles of each of these we have. So from our 4 grams of this stuff and our 20 grams of this stuff, we found out that we have 1.98 moles of H2 and 0.625 moles of O2. Note, here's another example of masses being misleading. We had way more mass of the O2, but in terms of a number, we have way more number of H2 because hydrogen is just so light. It's such a light element, 2 grams per mole for H2. That's not the whole story. The story is how much H2O can we make. So this is where the second step. So this is step 1. Step 1. Step 1. All right. Step 1 in our 3-step stoichiometry was going from grams to moles. Right? Grams to moles. If we look back over here, right? From grams, from mass to moles, we use the molar mass to get there. Now we're going to go to step 2. Step 2 is moles to moles. Moles to moles. And that's going to use the mole ratio. The mole ratio right there. Mole ratio, moles of A to moles of B. We can only do that in moles when we're working with moles. So I have my 1.98 moles of H2 and my 0.625 moles of O2. And what I want to know is I want to know how many moles now of H2O I can make. How many moles of H2O I can make. And that means I'm going to have to go through the mole ratio, right? Moles of this to moles of this. Moles of oxygen to moles of this. And this is what we were practicing in video 3.2. So what do I want on the bottom? On the bottom, I'm going to cancel H2, so I want my H2. On the top, I want my target, H2O. For this one, on the top, I want my target, H2O. The bottom, I'm canceling the O2. Those are going to come from the ratio up here, right? So for H2O and H2, it's 2H2 and 2H2O. It's 2 to 2. For the bottom, 0.625 moles of O2, we have our 2H2O, but it's only 1 O2. So we multiply this by 2 and this by 1. So this becomes 3, this times 2 over 2 is the same, so 1.98 moles of H2O. 0.625 times 2 is 1. I'm lazy for them. Times 2, 1.25 moles of H2O. So now we've gone to the next level. Right? We've finished level 2. We know how many moles of H2O each of these can make. That's part 2. That's part 2. So we've got from grams to moles. We've done our first step. Now we finished step 2. We've gone from moles of A to moles of B. And the last step is going from moles of B to the mass of B now. We won't forget the mass of water, which is what our question was actually asking us. How much water can we make with these starting materials? So let's finish it off. Step 3, going from moles now, moles of H2O to grams of H2O. So moles to grams, we have 1.98 moles of H2O and 1.25 moles of H2O. In this case, we know that water is 18.02 grams per mole. That was given. And we are going to multiply by 18.0. Oh wait, I need to change my color here. 18.02 grams per 1 mole of H2O, because that's what H2O's thing is. And we're multiplying by grams per mole because the mole is going to cancel the mole, right? The mole is going to cancel the mole. 18.02 grams per 1 mole. So we're multiplying by it. That'll tell us how many grams of water we are likely to make. How many grams of water are we likely to make? Well, we're just doing the multiplication, so 1.98 times 18.02, 35.68 grams of H2O on top, and 18.02 times 1.25, 22.52 grams of H2O on the bottom. H2O. So that's our 3-step. Number 1, figure out number of moles of our starting material. Notice it's the same chemical, H2 and H2. We've just changed the grams to a number in moles. Step 2 is the magic step where we can convert A to B, and we can only do that when we're working with moles. Remember, we can only do that when we're working with moles. 2 to 2. And then the third one, now we want something a bit more accessible than moles. We want to think what grams of water we're going to make, because hey, that's useful. We can know how much water we have in a normal kind of understandable mass. Then we're going from moles of water to the same substance, right? Same substance, water, same substance. And so we have worked through the entire system. Mass to moles, moles to moles, moles to mass. And we've used skills that we've already learned before to do it. We've just put it together now into this 3-step stoichiometry stuff. And we can figure out which is the limiting reagent now. When we look at this, this one, the 1.98, came from the hydrogen. This one, the 1.25, came from the oxygen. Hence, the oxygen is limiting how much water we can make. The 20 grams of oxygen, only makes 22.52 grams of H2O. Meanwhile, the 4 grams of hydrogen can actually make, if we had enough oxygen, 36 grams of H2O. Once again, mass is misleading. This 4 grams of hydrogen can make, with enough oxygen, 36 grams of water. This 20 grams of oxygen, with enough hydrogen, can only make 22 grams of H2O. But in terms of moles, it's okay. So that's one practice problem. We're going to do a second practice problem, so I'm going to pause and I'm going to set that up. So here's a practice problem, another practice problem. This is a theoretical yield problem. So we see here, what is my theoretical yield? Question is, I have 5 grams of C3H8 to start. My reaction is up there. Keep in mind, we can only convert using moles, and we want to go from this chemical to this chemical. We want to go from C3H8 to water. So looking at our little concept map, we've got the mass of A. A here is the C3H8. We want to get to mass of B. That's a theoretical yield, mass of B. To get there, we're going to go to moles of A, then to moles of B, then to mass of B. So let's write that out. So I have 5 grams of C3H8, and what I want to do is I want to take that 5 grams of C3H8 and I want to turn it into moles of C3H8. Right, that's my first step. The first step is to go from grams to moles. Then in my second step, when I get my moles of C3H8, I'm going to take my moles, however many moles I get, I'm going to leave a blank space there of C3. I'm going to write that in green. Moles of C3H8. Take whatever moles of C3H8, that's what I would have gotten at the end of my first step. And I want to, using this, go to I've got moles of A now, moles of A, I want to go to moles of B. So I want to go to moles of, what's my target again? Let me look at my question. Theoretical yield of water, of H2O. And in my third step, it should be in red, I want my theoretical yield, how much will I get in grams, so I want to start with the number of moles of H2O, and I'm going to finish off with the number of grams of H2O. So that's going to be my 3 steps, and in each step I'm going to take my end result and plug it into the next result. Now here's something kind of interesting. It's that the conversion factors here are not dependent on my answers, right? The conversion factors are, they come from the periodic table and they come from the reaction. So for example, this middle piece, this mole ratio, we already know the mole ratio. It's the mole ratio, moles of C3H8 to moles of H2O. Our conversion factor for this middle piece is going to be C3H8 and H2O. Which one goes on the bottom? Take a second. It's C3H8 because we want to cancel C3H8. C3H8. How many of them in my reaction up there? Just one. Just one C3H8. What am I looking for? Moles of H2O, amount of H2O. How many in my reaction up there? There's 4 H2O. So I can get that conversion factor without actually needing to know this answer, which is kind of cool. Or this answer. It's a tool that we use. It doesn't depend on what we're doing. Similarly, the conversion factor for down here, from moles of H2O to grams of H2O, is just the molar mass of H2O. And H2O we know is 18.02 grams per mole. We get that from the periodic table. We look over here, we have 2 hydrogens, 1 oxygen, we add them together, we end up with 18.02 grams per mole. Again, look up video 3.3, the previous video, to learn how to do that. Which one goes on the bottom? Well, moles. We want to cancel moles, so 1 mole on the bottom. We're multiplying by 18.02 grams per 1 mole. And my marker is dying. I think it's just because it's really hot in here, so all the ink is evaporating. And similarly, we have a conversion factor up here for C3H8. I don't know the molar mass of C3H8, so let me just get my phone to answer it for me. And we'll turn up the media here. Molar mass of C3H8.
The molar mass of propane is 44.1 grams per mole.
Thank you. So 44.1 grams per mole. So C3H8, I'm going to put that up here because that's what we're interested in. Right, C3H8 is 44.1 grams per mole. But of course, you can just do it in the table. It's 3 carbons and 8 hydrogens. So 44.1 grams per mole. We're going to be making that into a conversion factor to help us figure out whether we're going to multiply or divide. What goes on the top, what goes on the bottom? Well, grams is on top here, so grams should be on the bottom. Grams should be on the bottom, and it's 44.1 grams for 1 mole. 44.1 grams for 1 mole, or 1 mole per 44.1 grams. So we have our conversion factors. We have our flow, our 3 steps. Right? We're using this kind of thing. Step 1, step 2, step 3, and note that the conversion factors just came from our equation and from the periodic table. We didn't need to know the starting mass in order to get our conversion factors. So this piece could be 25 grams, could be 30 grams, could be 32 grams. We use the same conversion factors and we'll use the same flow throughout. And you'll see that this is true for any gram to gram conversion. You'll have different mole ratios, certainly. You'll have different molar masses, certainly. But you're going to be dividing by the molar mass, going through the mole ratio, and then multiplying by the molar mass of B every single time. So all that's left to do, and now that we've set it up, is to knock it down. All we have to do is now pull out the calculator and go through the steps that we've written out. We have 5 grams, the 5 grams of C3H8 that we started with. We worked out this conversion factor by using the table by 44.1 grams per mole, 1 mole per 44.1 grams. That's going to leave moles for us. So 5 divided by, because it's on the bottom, divided by 44.1, we got 0.113 moles. 0.113 moles of C3H8. And that 0.113 moles is what's going to start our next thing, 0.113 moles. Now we're in step 2 to go from moles to moles, and that's through the mole ratio. So we're multiplying by 4 and dividing by 1. So I take my 0.114 and I'm going to multiply it by 4, and I get 0.454. 0.454 moles of H2O. I actually kept the numbers in my calculator, so it's rounding for me. 0.54 moles of H2O. You guys might have 452. If let's actually stick to this 0.452 because I did times 4 divided by 1. Now that is the start of our third conversion. 0.452 moles of H2O, and I want my grams of H2O. I've already worked out what I'm going to do there, multiplying it by 18.02. So times 18.02, and I get 8.17 grams of H2O. And that's how you do it. That's 3 steps of a chemistry. We started with the mass of one thing, we finished with the mass of a different thing, and we had to go through all 3 steps to do it. And these are the same 3 steps that you're going to go through basically every time, with the extra side steps of actually determining the molar masses, right? Determining the molar masses of your chemicals. So that's the flow. And once again, mass is misleading here. We have 5 grams of this stuff, but because it combines with oxygen, you see that it combines with oxygen, we actually end up with 8.17 grams of water. So do watch out for that. Mass can be misleading. We're going to go to our last piece here, which is the theoretical yield and the actual yield. It's something called percent yield. So I'm going to pause and we'll get that set up. The last piece here is percent yield. This one's pretty intuitive, so I'm not going to spend too long on it. Theoretical yield will assume perfect conversion, right? When we did this, we assumed a perfect conversion from C3H8 to H2O. Nothing lost, perfect ratios, all of that stuff. But of course, in real life, nothing's actually perfect. So when we do them in real life, we actually get less than what we expect, less than our theoretical. And it's important in chemistry to figure out how much are you actually going to get rather than how much do you think you're going to get. And so when we do chemical reactions, we will often they'll often report a percent yield. What percent of the product is actually going to come out compared to what you put in. So here's an example of a reaction, right? Let's say I put in enough of this stuff to get 100 grams of this product, but this says 83% yield. So if I put in, even if I put in enough of this stuff that in a perfect world I would get 100 grams of this, I'm actually going to get 83% because of losses and side reactions and various other things. It's a percent yield. It's calculating it is just like calculating like a percent on a test. If you want to calculate what percent you guys got on a chemistry test, for example, you would put in the theoretical max mark, right, the maximum mark you could possibly get, then your mark up here, your actual mark, and divide it by each other times 100. That gives you your percent, right? If you got, I know, 15 out of a possible 20 questions, that's 75%. If you got 17 out of possible 20 questions, that's 85%, and stuff like that. If it's out of 30 questions, things get a little bit harder, but it's still the same calculation. So we do the same thing for theoretical and actual yield. The theoretical yield can come from these kinds of calculations, this 3-step stoichiometry stuff. The actual yield, well, you just have to do the experiment and figure that out and see what your percent yield is going to be. Yeah, so that's percent yield. Just to review what we talked about, because that's the end of the lesson. We talked about, once again, we talked about using moles instead of masses. This concept that mass ratio can be misleading, but mole ratio never is. We looked at the concept map of stoichiometry, which is very nice. I really like this slide. So, you know, it even tells you which video, gives you that basic thing. Then we did 2 practice problems that involve mass stoichiometry and determining the percent yield, which involved going from mass of A to moles of A, from moles of A to moles of B, and from moles of B to mass of B. So we had this 3-step thing going on. And then finally we had a short discussion about percent yield, how to calculate it, and why talking about a percent yield is important. Typically in chemistry we try to maximize our percent yield because it's more efficient. We can make more stuff with less starting material, it's cheaper, and so on and so forth. That's it for today. I'll see you guys in class, and we're going to do lots and lots and lots of these kinds of practice problems in class. All right, thank you very much.